Sir, can I ask a question over here of the previous
Yes.
class?
Yes, sir. Yes, sir. Please, please. I'm just going to open my notes. Just give me 1 minute. Yeah,
Yes.
please, please, sir.
Sir, the last class you have said that the signal having bandwidth of W,
Uh,
of that the sampling frequency will also remain W.
yes, sir.
So here I want to say that in case of our voice, which goes from 300 hertz to 3.4 kilohertz,
Uh,
including guard band, you can take it up to the 4 kilohertz.
mm.
So in place of sampling at 8 kilohertz, can we do at 4 kilohertz?
No, sir. No, sir. Sir. Essentially, it's a question of understanding how you define your bandwidth, sir.
So
Uh,
can you take some time to clear this
explain it.
part?
Yes, yes, sir. Yes, sir. Yes, sir. Okay. So if you have real signals, so one of the properties of real signals is if you, so x of t is a real signal. Okay. So if x of t is a real signal, it will show symmetry at the symmetry between the positive and the negative frequency. So suppose you have an x of t. This is in the frequency domain. I'm just plotting. You have the corresponding x of f, which is a Fourier transform. Okay. This is x of f. So if it's a real signal, then the real and then both sides of the origin. Sorry, 1 minute. Both sides of the origin, both of them are symmetric. So essentially, this part is symmetric to this part. Okay. So what to do is you generally consider the bandwidth of your signal as W here. Okay. So, but when you sample, what happens? So essentially, let me explain the sampling theorem once. It's very straightforward. Okay. So you take a symbol, you take a signal x of t. Okay. Suppose this was its Fourier transform. Forget about the W and other things for now. Let's just first understand the sampling theorem once. Okay. So x of t, and you are sampling at rate 1 by t. Okay. Or samples are spaced at
FS.
t distance. T time distance. Okay. So every time t you are sampling thing. Okay. So essentially x of t will become x of nt. Okay. So if you take the Fourier transform of this x of nt defined in some way, what happens is the spectrum would move. If this is if this is the baseband signal the signal that you're sampling, it will move by 1 by t. The whole thing will move by 1 by t, and you get a replica like this. And you get a replica. So essentially, at 1 by t you will get a replica. At 2 by t you will get a replica. At minus 1 by t you will get a replica. So on and so forth. Essentially, it will look like this. Okay. So the gap between this replicas is 1 by t. Okay. This is 1 by t. This is 1 by t, and so on and so forth. Is this clear? So if you sample something, so what you want to make sure is that this and this do not overlap. Yes?
Yes.
If they don't have to overlap, then what should be the thing? What should be the relation? The relation should be this gap should be greater than this width, no?
Yes.
Okay, so the gap should be greater than that width. Okay, that is your sampling theorem.
Yes.
Okay, so if you take your W as this for real signals, then the width will be 2W. But in general, for complex signals, what we do is we take this as the W, because in complex signals, things are not symmetric. In a complex signal, what happens is your signal may look like this.
Okay. Complex, it is not symmetrical, because of that whole bandwidth it is taken as that.
Yes. So essentially, 1 by t should be greater. So effect, always remember this: 1 by t should be greater than the width.
Yes.
Width of your total frequency content. That's all.
Frequency content.
Okay. Hopefully this answers, na sir?
Yes, sir.
Good. Okay.
Good experience, sir.
Good. So now we'll get back to OFDM modulation. Okay. So last class we were looking at the basic structure of OFDM modulation, and what else we will cover? We covered some properties of FFTs and IFFTs. Essentially, what we learned was circular convolution played well with IFFTs and FFTs, and we also looked at the basic structure of OFDM modulation. Okay, we'll just go through the transmitter once and then proceed onward. Okay, so we have bits which are mapped to constellation points. So constellation points are your complex numbers. You take n of this, do an IFFT. Okay.
Excuse me, sir.
Chitranjan, please.
Sir, you said that this is IFFT and FFT are mere representation in this block,
Yes,
right?
sir.
Then why we are not doing FFT at the transmitter side and DFT, sorry, IFFT at the receiver side?
So theoretically, nothing is going to happen. Okay, theoretically, you can do anything. It doesn't matter. You can do IFFT at the receiver and TRI-50 at the transmitter. There should be orthogonal to each other. But the idea is this. That's what I'm telling you. That the reason why they say IFFT at the transmitter is you always want to transmit a time domain signal.
That
Okay?
that means, sir, that will also work in this case.
Which one?
Means in OFDM, if we do FFT at the transmitter side and IFFT at the receiver side, that will also work.
It should work. Absolutely, it should work. But the thing is, the notation is always transmitter will do IFFT.
Okay.
Just I mean, it just to highlight the fact that the transmission is in the time domain and the mapping of the information in the frequency domain, because IFFT converts from frequency to time. It's just a convention. I mean, in the MATLAB and other things, if you replace IFFT by IFFT, nothing is going to happen. It's going to work.
Okay, sir.
Okay. I mean, IFFT and FFT are opposite to each other. That's the main thing in this whole chain, the receiver and transmitter chain. Okay. So now you have IFFT, which converts n input samples to n output samples. Okay. And then you do parallel to serial converter. This parallel to serial converter and serial to parallel converter again are logical circuits for us to understand. Essentially, you're taking n samples in and getting n samples out in one shot. Okay. Then you do something called cyclic prefix addition. Okay. After cyclic prefix addition is what you get your IQ samples. Okay. So now let us, let us get into the depth of this and try to understand a few things. Okay. The first question that we'll answer is, we'll forget about cyclic prefix for now, for just another half an hour, and then come back to cyclic prefix. Let's just look at IFFT itself. Okay. So, sorry. You have x of 0, x of 1, all the way up to xn minus 1. You are taking IFFT, and you are getting same some n samples. We call it a y0, y1. So if at any point today my audio is not clear, please let me know. I'll speak a little bit loud. Okay. My mic, my big mic was not working, so I'm using my laptop. So please let me know. So you do an IFFT and you get to this point. Yes. Okay. So now I want to understand how much is my time duration, how much is my bandwidth, and let's understand these parameters. What is meant by subcarrier spacing? Let us try to understand these few things. Okay. So these things are, so first of all, what is subcarriers? Let's talk about one. Subcarriers. Maybe I'll write this up. Okay. So the things in the frequency domain are called subcarrier. This is one subcarrier, this is second subcarrier. When this is zeroth subcarrier, this is the first subcarrier, this is n-1 subcarrier. Okay. So the inputs to your IFFT are called the subcarriers. Okay. So you modulate, you put your information in the subcarriers. Okay. So how did you map a constellation point? Each constellation point is put in one subcarrier. That's what we do now. That's what we do. So these are all subcarriers. Okay. So if you take an endpoint, I mean, so essentially, subcarriers are something that are defined. Okay, so this is called subcarriers. Okay, so let's look at a few things. First of all, learn how much is the time duration and other things. Okay. Suppose, so essentially, this is my time domain. Now, this is my time domain. This is what I'm going to pass it through my DAC. These are my time domain samples. Forget about CP for now. We'll come back to CP later. It's not a big deal. So these time domain samples are the one. What we are going to do, we are passing through our DAC, and that's what gives you an analog waveform that you, IQ sample. That's what is transmitted in the RF. Okay. Suppose your samples are placed t seconds apart. Okay, so your sampling rate is 1 by t. Your sampling rate is 1 by t. So you essentially y of 0, y1 are discrete samples. They're coming and you're putting into your DAC. Okay, so you have to assume some sampling time. Let's assume the sampling time is t seconds. So, and this is your OFDM symbol. This is one OFDM symbol. Okay. So what is the duration of the OFDM symbol in terms of T? What's the duration of the OFDM symbol?
NT.
NT, fantastic. So there are n such samples, and each sample is t seconds. Okay, the duration of the sample OFDM symbol is n samples. Okay. What is the bandwidth of the signal? Remember,
NT.
no, sir. Because your samples are placed t seconds apart, your bandwidth will be 1 by t.
Okay, okay,
The
yes.
OFDM symbol is a bigger thing. Okay, so your samples are t seconds apart, so your bandwidth will be this is equal to your W. Agreed?
So bandwidth of one subcarrier you are talking.
No, bandwidth of the entire signal. See, this is something that we have to get a little bit clear. Okay, so your OFDM symbol is a combination of, that is what is the terminology. OFDM symbol means there's n samples together, but your samples are placed t seconds apart. Yes, your samples are t seconds apart. So t seconds apart means essentially the entire signal bandwidth will be 1 by t. Okay, so let me tell you what this NT would correspond to. Okay, so suppose this so essentially your bandwidth is
So
W, no?
this T is one symbol period, or it is kind of
Sample period, it's a sampling period, not symbol period. OFDM symbol is this.
okay.
Okay, so let me just draw this diagram a little bit more carefully. Okay, so you are getting the output of FFT will be Y0, Y1. Now you are going to get something like this, Yn minus 1. Okay, and this will go through your DAC. Okay, this is going to your DAC. Okay, so what does DAC require? DAC has to has one of the inputs of the DAC is the time period. Okay, at what rate? Yeah, this is what is the gap between these two samples, time sample. I mean, in discrete domain, there's no gap actually, but this is what we say. We say we give this input as time period to this. Yes. Then in the analog domain, what it will do? It will make sure that these two samples are separated by t and does an interpolation between these two. Okay. So when you do this, the bandwidth of the signal would be, the bandwidth of the output signal will be 1 by t. Okay. I mean, we interpret this whole thing as an OFDM symbol. The whole thing as an OFDM symbol. But
Sir, just now you have also told in the beginning when I asked the question, you have explained it that if the signal is having bandwidth of W, then it's the time of the pulse will be 1 by t. The similar thing over here, you are telling it right now.
yes, exactly. Okay, so your sampling rate, your sampling duration is always once the inverse of the bandwidth. Okay, so the bandwidth will be inverse of your sampling time. Okay, so the bandwidth of the signal is W. Okay, so now let's get into frequency domain. So this is my frequency domain. Yes, this is my frequency domain. So when I have my frequency domain, now the entire bandwidth. So what is the bandwidth now? W. Okay, and this is what I told my subcarrier. Okay, so what is the bandwidth of each subcarrier?
W by N.
Yeah, is equal to W by N. This is equal to 1 by NT. Okay.
Yes.
So 1 by NT is also, so this is called subcarrier spacing. This is very important. Okay. It's also called SCS. If you look at the specification, it's called SCS, subcarrier spacing. Okay. So I'm going to denote this as delta F. The subcarrier spacing is delta F. Okay. So essentially subcarrier spacing is nothing but what is the bandwidth allocated to each subcarrier. Okay. So what is the bandwidth that's allocated to each subcarrier is called subcarrier spacing. Is that clear?
Yes, sir.
Okay. So now let's put all of this thing together once. I'm going to write this here. Maybe I'll just erase this one. Right? Okay. let's start with subcarrier spacing. Subcarrier spacing, delta F is equal to 1 by NT. Okay. OFDM symbol duration. OFDM symbol means always the n things together in the time domain. This is the okay. Symbol duration is equal to
NT.
Yeah, so this is equal to 1 by delta F. Okay. Time duration between samples is equal to 1 by T is equal to sorry.
T, it is T, sir.
T, yeah, so is equal to T is equal to
1 from W.
1 by N delta F is equal to 1 by W. Okay. So alternatively, I will write sampling frequency is equal to N times delta F. Okay. So now let's look at this. So now let's look at this. So what is the time duration? So essentially subcarrier spacing is equal to delta F is equal to 1 by NT. So essentially I'm trying to put everything in terms of delta F. I want to remove T. So OFDM symbol duration is 1 by delta F. Okay. So what this implies, if your subcarrier spacing is, so OFDM symbol duration means essentially the time you have to wait till you can decode. Okay. You have to get those N samples before you can decode in the receiver also. Okay. So that determines your latency. You understood this? So you're transmitting N samples. Only when you get those N samples, you can do an FFT at the receiver and decode it. So that will be your minimum latency of the system. Okay. So if you have so essentially that's inversely proportional to the subcarrier spacing. So if you have a higher subcarrier spacing, then what happens is you have lower latency. The duration is lower. That is the reason why a lot of different subcarrier spacings were introduced.
Can I just to understand? So for example, if I have say 300 subcarriers of 15 kilohertz subcarrier spacing each, so that means my sampling frequency has to be 4,500 kilohertz, right?
Yes, sir. Yes, sir. Exactly.
Is that correct?
Exactly.
Okay.
At least 4,500 kilohertz.
If it is more, then it will better.
Yeah, it's fine. Yeah, okay. We'll actually talk about that one also, more or less what's the correct thing. Okay, so let's look at LTE once. If you look at LTE, we have only 15 kilohertz subcarrier spacing. Okay, so what will be my what will be my OFDM symbol duration? Will be equal to 1 by 15. 1 by 15 into 10 power 3. Yeah, I don't know how much is this. Okay. Let me just do a quick calculator. 1 minute. Zero 0.066 milliseconds.
66.67 milliseconds.
That's okay. Yeah.
66 microseconds. Okay, approximately 66 microseconds. Approximately, yeah, 66 microseconds. Okay, so in LTE, what happens is you have to at least wait 66 microseconds before you decode. Why? Sorry. Because you're sending N samples. These N samples have to be collected at the receiver before you can do your FFT. Only then you can decode your data. Na? Yes. So that is the minimum thing. So in NR, 5G NR, what they did was they introduced multiple subcarrier spacing. One is 15, one is 30 kilohertz, one is 120 kilohertz, one is 240 kilohertz. Okay. So 30 kilohertz, what will be your OFDM symbol length? It will be half of this, 33 microseconds, approximately. Again, approximately. At 120 kilohertz, it will be 33 by 4. Okay. At 240, it will be 33 by 8 microseconds. Okay. So one way of effectively reducing the latency in the system is to increase your subcarrier spacing. Okay. The main idea behind that is the OFDM symbol duration is inversely proportional to the subcarrier spacing. Always remember this. Okay. So any questions before we proceed?
So then the number of subcarriers will be reduced, right? As we are increasing the subcarrier space.
The number of, for the same bandwidth, yes.
Okay,
For the
then
same-
it may be problematic in the frequency selective fading. Oh,
Wait. Let's not go ahead. I'll tell you that. I'll tell you how they design it. Actually, it's a little bit different on the design aspects of what do you say, LTE and 5G. They not define the bandwidth like that. Okay, I'll come to that point.
okay.
So the main the things that you should remember always here in this point is OFDM symbol duration and the sampling. I mean, some of this. I mean, you understood how to get the values. No, you should be able to derive them anytime you want. It's not a big deal. Okay. So now let's look at time frequency grid. What I mean by time frequency grid? Okay, so time frequency grid is actually a workshop. It's a concept more than a physical quantity. It's a concept. Okay, it's very important concept though. Okay. So now what we are doing in the frequency domain, we have n subcarriers. So this is n subcarriers in the frequency domain. Okay, you take your IFFT. What you get is again n samples. This is n subcarriers and samples in the time domain. Okay, so it's not like you are going to stop after sending n subcarriers, n samples. You're going to go on doing this forever. Yes. So what you do is, so next time, this is the first time that you are sending this. Next time also, after this is sent, what will happen? You'll have again n subcarriers. You do an IFFT and then you transmit n samples. Okay. So how they represent this is, they represent this in a very weird manner. They draw a two-dimensional grid. One is called the frequency axis. Sorry, this is the time axis. Okay, this is the frequency axis. Okay. Okay. So essentially on the vertical axis, so essentially the way they think, you have to think about this is just an interpretation. So these are your subcarriers. Okay, so this will be your zero. I mean, it depends on the top or bottom. This will be your zero subcarrier. This will be your first subcarrier, second subcarrier, so on up to n subcarrier. This is your OFDM symbol. So this is one OFDM symbol. So the interpretation is that this whole thing would correspond to one OFDM symbol after you do your IFFT. Then the next one you transmit is the second OFDM symbol. The third is this third OFDM symbol. This is the fourth OFDM symbol, so on and so forth. Okay. So this is the subcarriers. Okay, this is the symbols. Okay, so this will be my first OFDM symbol. This is my second OFDM, zeroth OFDM symbol. This is my first OFDM symbol, the second OFDM symbol, third, so on and so forth. Okay. So essentially, before doing IFFT only, they're just calling this n sub. They're assuming that you're going to. So how does this finally pan out? So the way it is going to pan out is you're going to take the IFFT of this whole thing, and that's going to come like this. Okay, and the second sim, then they're going to take the IFFT of this, and that's going to come as this. The third thing, and that's going to come as this. Okay, that's how you interpret that. Is this clear?
Yes.
Yes.
Okay, so this is a very important concept, because everything in the standard is put in this time frequency grid. Okay, so again, let me just repeat. So on the x-axis is your time, on the y-axis is your frequency. Okay, the interpretation of each grid on the vertical side is that each of this is a subcarrier. Okay, each of this whole thing is one OFDM symbol. So essentially, this is your first OFDM, this is your first OFDM symbol, this is the second OFDM symbol, third, fourth, fifth, sixth, seventh, eighth, something of that sort. This is your time duration. Okay. So effectively, if we take the example of LTE, there are 15 kilohertz SCS now, 15 kilohertz SCS. Okay. So what's going to happen? So this gap is 15 kilohertz. Okay. The duration of this would be 33 microseconds. Maybe I'll write this properly. Just hold on. Okay. So this gap is 33 microseconds.
66 microseconds, sir, for 15 kilohertz.
Oh, sorry, 66 microseconds. Sorry. Yeah. It will be 66 microseconds. Okay. It's not like this is just 1 by n of 66. It's just the whole thing is interpreted as 66 microseconds.
Is 15 kilohertz for only one subcarrier, sir?
So every subcarrier is 15 kilohertz.
Okay.
So each of this is in 15 kilohertz. That's what you know. I'm not putting all that. So how many other subcarriers are there?
Yeah, I think you should clarify that this is subcarrier spacing, not the carrier itself. I think that was a confusion.
Yeah. This is the subcarrier spacing. So this is your subcarrier spacing. Okay.
Okay, sir.
And this is your OFDM symbol length. OFDM symbol length. Is that fine? Okay. Any other questions before we proceed?
No, sir, it is fine.
Okay, good. Okay. I'm just going to. Okay. Okay. So since we drew the grid, what I'm going to do is I'm going to since we drew the grid here, and let's just explain one simple concept, and then we'll go ahead. Okay. So one of the main reasons one of the things, the important things that we thought that that's required for the base station is multiple access. It should serve multiple users. Okay. And we saw both TD and FDD where resources are separate in time and resources are separate in frequency. Okay. So now in OFDM, what are your resources? Your resources are both in time and frequency. So your resource grid is a set of resources available to you. Yes. Your resource grid is a set of resources available to you. So what can you do? You can say that I'm going to give this set of resources to one user. Okay. I'm going to give this set of resources to second user. Okay. I can do whatever I want. This is my set of resources that are there available with me. I'm going to give this set of resources to another user. Maybe this set of resources to another user on this grid. Okay. That is how you do multiple access in OFDM. So in the time frequency grid, you fill up your data. Okay. And that's how you separate out users. So when you give this time and frequency bin, so for example, you give this set of frequencies to a particular user, okay, or in this particular time instant, in this particular OFDM symbol, the user will only, so that does not conflict with any other user put in other parts of the grid. Yes. Okay. So it's a combination of both FDD and TDD when you do multiple access. Okay. When you do multiple access, essentially it's a combination of FDMA and TDMA. Sorry, not FDD and TDD. Sorry, FDMA and TDMA. Okay. You are separating out users in both time and frequency, but you are using the time frequency grid to do this.
Sir, is it kind of dynamic allocation?
It will be dynamic. So essentially, we'll come to that when we do the spec. But answer is yes. It will be very, very dynamic, depending upon the number of users, depending on the channel, all these things. You can choose anything in the grid to give to any user. It is with single antenna. With multiple antennas, you can even overlap them, but that's for something else. We'll talk about that later. Is this concept clear?
Sir, is there any concept of guard band here?
Guard band, there's no guard band. So essentially at this moment, there's no guard band. Now, I clearly told you how to do this. So I have my IFFT. So this is what we are doing. Every time I'm taking my IFFT, only thing I'm doing is cyclic prefix addition. I haven't told you about cyclic prefix addition. We'll come back to that later. Okay, I'm transmitting. I once finished my first OFDM symbol, I'll transmit my second OFDM symbol. I transmit my third OFDM symbol, so on and so forth. Okay, in the frequency domain, there's no guard band, at least to the between the users.
Sir, if between the users means just for understanding in this grid, is there any no overlap or something?
There's no, let's assume a single antenna system to keep things simple. If you assume a single antenna system, there will be no overlap between two users. For example, I will give this set of resources to one user, user one. Okay, I'll give this set of users to user two. So what will user one do? User one in the third OFDM symbol, the last the two subcarriers are allocated to him. He'll somehow know that. Suppose he somehow knows that, he will decode only these two. He'll decode only this part. The second user will decode only this part. He'll get information from everything, but but his information does not overlap with other people's information.
May I answer this in a different way to him, in case you allow?
Yes.
Yeah.
Please.
Let's take an example that we have 5 megahertz bandwidth in total. So what you do is that first, I mean, from that 5 megahertz, from both sides, you remove some guard band of some kilohertz, 60, 70 kilohertz perhaps. And then you divide by, say, 15 kilohertz subcarrier spacing, then you divide by 15 kilohertz, and say you get n number of subcarriers. So in terms of frequency, you are having guard band in the entire bandwidth, which is being divided into subcarrier. And here, when you go into the time domain, that is the symbol duration. So perhaps sir will tell later that we have cyclic prefix to take care of kind of a time domain guard band.
Yeah. So that's absolutely correct, sir.
Sir, is it required to be continuous allocation of the particular resources block to the one user, or it can be allocated in discrete manner also?
It can be allocated in discrete manner. So the specification allows that, sir. The specification does allow to allocate user one to be here and here and here also. It allows that. Okay?
Maybe we can answer that. Of course, theoretically it's a random, but there are certain things once we go to LTE or 5G specifications, there are certain, I mean, some of the time slots are fixed for some of the, say, signals, either control signal or you can start a traffic signal from particular symbol only. So those limitation would come when you go to the specification, but theoretically, yes, it's a random.
Theoretically, yes, sir. Theoretically, yes. The specification also allows. So finally, it's up to the base station, sir. Base station. So if the problem is you implement here, it will become difficult for the user to decode also. Okay. So generally they do a continuous allocation, but specification does allow. We'll talk about all these things in detail. What are the restrictions on the allocations? What are the different types of allocations and all this? Okay. Okay. So now let's go to the next topic. Okay, cyclic prefix. We'll come back to the time frequency grid. I mean, the whole standard is about filling the time frequency grid. We'll come back to that. I just wanted to put that here so that I don't have to spend time when we do the standard. Okay. So what exactly is cyclic prefix? Why do you require cyclic prefix? Okay. So cyclic prefix, remember, cyclic prefix is added in the time domain. Okay. So if you go back to your system diagram, so after IFFT is when your cyclic prefix is added. Your cyclic prefix is added here. Okay. So you already got your time domain samples. Okay. And you are adding cyclic prefix. First, let's see what is cyclic prefix and why is it useful. Okay, so that's what we're going to now talk about. Okay, so you have your X0. Okay, I'll write it another way around this one. X0, you are sending to IFFT. What you get? You get n samples. Okay, so maybe I'll add a few more bits. You get n samples. So what exactly is cyclic prefix addition? Okay, cyclic prefix takes cyclic prefix takes to one parameter. Okay, cyclic prefix called cyclic prefix length. cyclic prefix length. Okay, I'll call it as L. In terms of samples, let's put L samples for now. Okay. So what that means is, essentially, you are going to take L samples from here and copy them to the front. Okay. So again, just let me repeat it. So essentially, you take L samples from the back side and copy them to the front. Okay. So remember, this was very, very simple, similar to the way we were doing cyclic convolution, where we copied the whole thing on the other side. Okay. Instead of copying the whole sequence on the other side, I'm just copying L samples to the other side. Okay. So, okay, let's take an example. Suppose you have your FFT size was 8. Okay, so you have Y0, Y1, Y2. This is your output, Y1, okay, Y7. Okay. Suppose your cyclic prefix CP length is equal to 4. What do? You copy the last 4 samples to the front. So essentially the output of the cyclic prefix addition will be, you'll have it something like this, Y7, Y6, Y5, and Y4. So this is your cyclic prefix. Okay, this was your original OFDM symbol, and essentially you copied the last few parts to the front. Okay.
So you mean some of the samples from the end you are adding at the beginning, right?
At the beginning, yes. The last few samples.
So when we say last few, is there any standard how much or
how much? Yeah, that's defined by a standard. So that's called cyclic prefix length.
No, that's okay. Standard. They are defining the time, but is there any logic behind that?
Yes, there's a lot of logic. I'm going to explain that. Okay. So for now, I just want to understand what is meant by cyclic prefix addition first. Okay, cyclic prefix addition is nothing but you take the last few samples and add to them. Okay, we'll specify the length of the number of samples that you should add. I just gave an example of 4. If your cyclic prefix length was 3, then you just add 5, 6, 7. If your cyclic prefix length was 5, you add Y3, Y4, Y5, Y6, Y7 to the front. Okay, so this is the operation of cyclic prefix addition. Is operation clear?
So will it increase the symbol period? If symbol was say whatever 66 microseconds, so will it increase the symbol period?
So effectively, one thing that you should notice is, as Mr. Ashok Kumar has pointed out, so this is useless information. This information is already here, but you are just adding them. It's redundant information. Okay, but this is necessary. So this is a waste of your resources. Okay. So your OFDM symbol now is, this is original OFDM symbol. Now you also have something called cyclic prefix. So now how are you going to transmit? You're going to transmit cyclic prefix, the next OFDM symbol. Okay, cyclic prefix 1, OFDM symbol 1, cyclic prefix 2, OFDM symbol 2. Okay. So for the first cyclic prefix, what did you do? You copy. So this and this part are the same. Similarly, this and this part are the same. Yes, so you're effectively increasing your.
So every symbol, can we have different kind of CP?
Different kind of, sorry, last word, sir.
Different kind of CP, that cyclic prefix.
Different length you mean?
Different length.
Yes, sir. That's also part of the standard. So what happens is, I will tell you, but generally you keep them the same. There's a minimum length that is specified in general.
So I think during symbol 0 we have a slightly bigger CP, yes, and then we have standard one.
Standard ones later, exactly. That's correct.
So if you keep the same, then every OFDM symbol, that CP is getting repeated. So it is not the same thing is getting repeated, and then it is the wastage of that.
No, sir, it's not the same thing, sir. So OFDM symbol 1 will have different data. So this will be copied here. This will have different data, so this will be copied here. Okay.
Okay. Yes.
Okay. So Sai Predi is asking, why can't we append a few zeros? First of all, why did I append this one? Let's first deal with. Let's talk about this. Okay.
I think redundancy improves reliability also.
It improves reliability, sir. But the main reason is, I'll just explain you now.
So the main purpose is ISI. That is the problem. But here, since the information is, we are adding prefix and suffix both, so that can be utilized for improving the reliability. I don't know.
In some sense, yes, sir. Vijay Kumar, Roy sir, essentially in some senses, actually it's very helpful to, I'll tell you all the uses of CP. It's actually pretty, I mean, without CP, the whole system will fail.
Right, perfectly right, perfectly right.
So let's assume this. So this is your OFDM symbol 1, okay, followed by, I'm telling you the first use of CP, okay, symbol 2. Okay, so now we have seen multipath. Yes, we have seen multipath. Essentially, multipath, what will happen? So you will get, so if you, because of multipath, what you're getting, you're going to get this symbol now. Let's forget about attenuations for now. Let's just look at the time delays. Okay, the next OFDM symbol will come after certain delay. Okay, the same thing will come. So this was the direct path. For example, this is path 1. Okay, the next one might have hit a reflector a little bit far away and come. So essentially, what will happen? This will get delayed by a little bit. Okay, so this is the delay in the paths. Okay, the next path might have been having much more larger delay. Okay, same, this is symbol 1, symbol 2, symbol 1, symbol 2. Okay, so now what is happening? Because of multipath, your OFDM symbol 1, so now what do you get? You get the output, the addition of all this, na? Addition of all this is what you're going to see.
Certainly.
Yeah, with some alphas and betas and gamma, I mean, with some coefficients. Okay, let's forget about the coefficients. That's not important for the discussion. So now your OFDM symbol 1 is actually interfering with OFDM symbol 2. Yes?
Yes.
So how do we avoid this? What are the different ways of avoiding this? Okay, one simple way of avoiding this is I could have put a guard in the sense that I will send symbol 1, then I will send a bunch of zeros, like how Sai Pranay told. I'm going to send a bunch of zeros. Okay, and then I'm going to send symbol 2. Okay, so now what is going to happen if I have multipath? This will come here. S1, zeros, symbol 2. Similarly, this will be here, S1, zeros, symbol 2. Okay, so now what is going to happen? Now S1 is interfering only with zeros, which is anyway we are going to throw it away. Okay, it's not interfering with S2. Okay, so at least with this interpret, so instead of at least one thing that we require for sure is to handle multipath, you require something between symbol 1, OFDM symbol 1 and OFDM symbol 2, either zeros or something else. Okay, for example, let's take zeros. If we take zeros, what should be the length of this? Can anyone tell me?
Maximum delay of the multipath?
Yes. Okay, so the number of zeros or the duration of zeros, number or I'll call duration, should be greater than the delay spread of the channel.
Yes, yes.
Okay, or the length of what you call it as the length of the channel. I mean, it's more technically we call it the delay spread of the channel.
Right.
Delay spread of the channel. Okay, so essentially delay spread means essentially if you have the multiple taps like this, what you do is, I mean, there may be one more tap somewhere with very, very low energy. You neglect that. You almost make sure that all the things with the high energy, this gap, this duration is called the delay spread. Okay, so at least you should understand that the number of zeros, the duration should be greater than the delay spread of the channel. Okay, so this is very important. This is also the guiding principle of the cyclic prefix line. Okay, so why cyclic prefix instead of zeros will become clear in next minute. Okay, so one thing is important, that you could have put zeros, but this is a waste of resources. You are not transmitting any additional information there. They're waste. Okay, so number of zeros should be greater than the delay spread of the channel. Okay, good. That's one point to remember. Is there a concept of adaptive CP length depending on the channel? No, generally you don't change CP length because of implementation issues. You don't, but theoretically, yes, you can adapt your CP length. Okay, but Ashif, you can adapt your CP length, but generally you don't do it. It's too complicated to implement. Okay, so the second point, equalization. Okay. Now you have your OFDM symbol. OFDM symbol 1. Okay. Call them as y0 to yn minus 1. Okay. Now you are passing through a multi. So finally, you are transmitting it. When you transmit it, it is actually going through a multi-part channel. It's an LTI system. Okay. So this is going to a channel with certain impulse response. Okay. Call this some h of n. Okay. Some h1 to hn. Okay. Some sequence. Okay. So what you get at the output of the channel is not circular convolution, but linear convolution. Yes.
Yes, yes.
Nature does not do linear circular convolution. I mean, it's an LTI system. You're passing some samples to it. So automatically, what will the output? The output would be y linearly convolved with h.
This is circular, I think.
So if you just pass through multipath, what you get is you're getting delayed versions and adding up. It's not circular convolution. Now at the receiver, you are doing what? You're doing FFT. When you do FFT, linear convolution will not give you it will not separate them as multiplication. Nah? It will not separate them as multiplication because it's linear convolution. Okay. So now the question is, how do I engineer my system so that it goes to a linear convolution, but the output is circular convolution? This is exactly what we have discussed when I did this thing. How do you convert linear convolution to circular convolution? You just periodically repeat it. Yes, I just took the old one here and I just put it in front. And I did linear convolution. When I did linear convolution, I get circular convolution. Okay. So what you do is, instead of transmitting this, suppose I transmit, sorry. Okay. When I pass this channel, what happens is the output would be, so suppose I pass this channel, the output would be, and nicely, as long as the length of the channel is less than the number of repetition, this length, number of taps in this channel is less than the number of taps in this channel is less than this length. What the output I will get is, output will be nicely y circularly convolved with h. You can check this out. Okay. So this is exactly what I told before. To convert linear convolution to circular convolution, all you have to do is you have to repeat the samples. Okay. And the repetition length, the number of samples you should repeat from the back to the front should be at least be as large as the number of taps you have in the time domain.
Just an interesting question for the development of this circular convolution.
Yes, sir.
First, it was developed mathematically, then it was deployed, I think, practically. What is your opinion?
Sir, circular convolution was known from a long time.
No,
okay.
No. Use of circular convolution for
OFDM.
OFDM, yes.
Yeah. So it came later. So first the theory came and then they used that.
Yes, yes.
So there was one question. Does the CPU also add diversity gain? It has diversity gain, but you generally don't use that. You use CP for something else. Next point, I'll tell you this next point. But at least this point, is it clear? So why one of the other uses of CP is CP converts linear convolution to circular convolution. Okay. Again, the CP length should be greater than number of taps in channel. Okay. So with this one combined with two, one anyway you're putting zeros. So, and for equalization to become easy so that you can use FFT properties properly, you require to repeat. So instead of putting zeros, what they do is they repeat. So what you do, you repeat this whole thing here. When you repeat this whole thing here, at the receiver, you drop those things. Okay, repeat. In the receiver, you're dropping your cyclic prefix. Instead of dropping zeros, you're just dropping your cyclic prefix. But because of the cyclic prefix, what happens? Now you're getting circular convolution instead of linear convolution. Is this concept clear?
Yes.
Okay. So that is the second use of circular convolution. Okay. Sorry, the second use of cyclic prefix. So now I'm going to tell you one more use of cyclic prefix, and then we're going
One
to stop.
more question. Just delay spread due to multipath. Is does it depend on the sensitivity of the receiver also?
No, sir. No, sir.
Because if the received signal, the handset which receives signal, if the sensitivity is limited in their case, so so many paths are there. Suppose.
Yes, sir. So I understand what you are coming. You are saying that if one tap is very low power, will you be able to resolve that?
Right.
Yeah. So essentially, it's a question. It's more of a question of your SNR rather than anything. The question you asked is very, I mean, actually, very deep question. But does it depend on your receiver sensitivity in a very non-linear manner? Yes. But generally, you don't talk about that because by the time the power will be so low that you can neglect them.
Thank you.
I mean, if your signal is at the receiver sensitivity, you will be mostly noise limited than any of these issues.
Okay.
The third point. Okay, another question is, so this is kind of overlap save method for circular convolution. Yes, that's absolutely right. Okay. So the other issue is this. Okay, I'm going to tell you this. This is a more practical thing. So you're sending your symbol one, OFDM symbol one. OFDM symbol. Okay, one symbol of n things. Okay, and followed by symbol 2, and so on and so forth. You're transmitting it. Okay, so when you transmit in the time domain, you're transmitting sample continuously. You're transmitting it. In the receiver, what happens? So when we drew the block diagram, what did we say? I mean, we made an inherent assumption here. Okay, that's not very visible. Okay, so you're taking this n samples, and the same n samples are being fed for the FFT. Only then this FFT will get the IFFT get inverse of each other. Yes. I mean, you're taking this n samples and you're taking this n sample, you're taking this passing through this FFT, the FFT and IFFT cancel, and you get back whatever you transmitted. Okay. But practically, what happens? Okay, there is some other symbol 0 here. Okay, symbol 0. Okay, practically, what happens? You're transmitting this waveform. Okay, S0 is coming, then S1 is coming, then S2 is coming. It is coming in continuous samples. You don't know where is S1, where is S2. Okay, essentially, you get a bunch of samples. You're getting one sample after another, one sample after another. Okay. You will have some timing algorithm to say that, okay, this is the start of your OFDM symbol. Let's assume that there's a timing algorithm that gives you the start of the OFDM symbol. Let's not worry about that right now. Okay. From that point, what do you do? From that point, suppose your FFT size is, let's say, 1024, for example. You will take 1024 samples. Then you know that the next OFDM symbol is coming. You take 1024 samples. Okay, and so on and so forth. Let's assume there's no CP for now. Okay, let's see what is the problem with that. Okay, so this is all well if your timing is exact. So if timing is correct, then you are good. Okay, what happens if your timing is little bit wrong? So instead of your timing algorithm giving the exact timing here, suppose it gives a timing here, 2 samples or 3 samples apart. I mean, that might be called because of noise, so many things we don't know. Okay, 2 samples timing error is an engineering issue. Okay, suppose there's some timing error. Then what is going to happen? You're going to start at this sample, collect 1024 samples. Okay, then collect 1024 samples. Okay, and then do your FFT. When you do that, what happens? You're going to get some errors now, because this, whatever is there here, is the information of the previous symbol. It has nothing to do with this FFT. The previous, the symbol 1 is AFFT. You understanding? Okay. So effectively, at this point, what you require exact timing. Exact timing is almost, it's very, very difficult for low SNR and mediumly difficult for high SNR. Even at the very high SNR, you'll always occasionally miss timing. You can never get the exact timing at any point. It's not a good engineering practice to assume correct timing. Okay. So how will cyclic prefix help in this problem? Let's see this. Okay. Now I'm going to draw the same thing with cyclic prefix. CP1, symbol 1, symbol 2, CP2, CP2, symbol 3. Okay. So ideally, I want to lock at this point. This is my ideally locking point. Okay. So let's assume some numbers also so that we can talk easily. So let's assume this is 1024. This is maybe some 64 length CP. Let's say I'm just giving some examples. I mean, there's nothing. 64 is the length of your CP. Okay. So suppose you do this. Then what happens is, so then everything is fine. On the other hand, suppose you come here. Okay. Suppose your timing, instead of coming here, it came here. Then is it going to be a problem? So from what are you going to do from this point? You're going to take 1024 samples. Then you're going to neglect the CP length. And from here, you're going to take 1024 samples. Then you're going to neglect CP length. And then you're going to take 1024 samples. Okay. So now let's zoom into this picture. Okay. So you have CP, you have OFDM symbol. So if you start from here and take an FFT, we all know what happens. But what happens if you start at this point and take the same FFT for 1024 samples? What are you going to have? What is going to happen? Can you even tell me? You understood what the problem is. So what I'm trying to say is, instead of starting your FFT at the exact boundary, if I start it a little bit left into the CP and do a same 1024 FFT, okay, the original length also was 1024, remember, then what is going to happen?
So you will get the same result because that the CP is nothing but the repetition of that what at the back we have given at the beginning.
Yes. So what is going to happen is you are not going to get any information loss because technically this is the same information as this. Okay. But to not get the same output, that's different. I'll tell you what is output you're going to get. You're not getting the same output, but you're going to get output from which you can recover your data. Okay. So what are you going to get? Okay. Let's see this. We already actually looked at this. So I'm just going to go a little bit ahead, backwards, and show you what are we going to go. Sorry, 1 minute. Okay. Remember the circular shift. Okay. So circular shift is nothing but just shifting it circularly. Yes, just shifting it circularly. When you take the FFT of a circular shift, what you get is you get the original one into some multiplicative factor. Okay. We'll use this idea now. Let's see what happens. Okay. Remember, let's just write this up. Okay. So essentially, I'll have y0, y1, y1021, y1022, y1023. Okay, so my cyclic prefix will be y1023, y1022, y1021, y1020, so on. Okay. So ideally, what you wanted to do, you want to start your FFT here, take 1024 samples and do it. Then you'll get your input, whatever you have inputted there. Okay, let's say that is x of k. Okay, but now instead of that, I'm starting at this point. For example, I missed by one sample. Okay, so I'm going to take my 1024 FFT for these samples up to 1022. That is nothing but a circular shift of this of the original sequence. Huh? That's exactly a circular shift of the original sequence by length 1. Yes. This was your original sequence. Look at that and compare with this. The same thing as the previous one, except that it shifted cyclically by 1. This 1023 came here. That's all. Okay. So when you take an FFT of that, what are you going to get? Now you're going to get x of k into, because it's an FFT, it's an FFT, na? Yeah, you will get e power minus j2 pi by 1023 into 1 into k, because it's one shift. Okay, so the original thing is there, except that now it's getting multiplied by some phasor factor. Okay, how this is taken care in the receiver, I'll tell you when we do channel estimation, this will automatically be taken care of. Okay, but one thing you should remember is, because of this, you're not losing information like this. Here, you'll not be able to recover this because it's not a circular shift. You are getting interference from the previous symbol. Whereas here, as long as my timing is inside the CP, you're fine. Okay. So now let me ask you one question. Is this clear?
Sir, I think in the exponential, the N is 1024, 1023.
1024. Yeah. Sorry.
Thank you.
If FFT starts at y of 5, sir, missed by some 5 sample.
Okay. So the question that he is asking is, 1 minute. What happens if I start here? Yes.
Yes.
Then you're in problem. So what should your strategy be? The strategy should be whatever your timing algorithm tells. Okay, suppose your timing algorithm will tell you an output, will tell you where your OFDM symbol starts. Yes.
Yes.
Okay, let me just erase this and then I'll tell you what to do. Okay, it will tell you some. It will tell you something. It start here or start here. Whatever you do, you always add some number and go to the CP so that you are safe. Okay, so even if it tells you you are here, don't take it here. You always say that I'll go to the left by 6 places. Okay, so even if you are here, but when you do the 6 places, you may end up in cyclic prefix. You always start at 6 places to the left.
But but in actual at the time of implementation, if you go back at that time, some other signal will be there.
No, so cyclic. You are in the cyclic prefix now.
No. See, but for this symbol, okay, I am in cyclic. But just at that point of time, before that, another symbol was there. But if I go back for that.
Okay, yes, sir. Okay, let's see. I'm assuming that your timing error, for example, your timing error is decent and is less than some cyclic prefix length by CP length by 2 at least. I mean, your timing error should not be so bad. Okay, so it can be at most maximum CP plus or minus 2 by 2.
Okay. Then it will be okay, yes.
Then, or CP by 4. Generally, the timing error will be off by 3-4 symbols, sir, not more than that. Okay, so that if you start here also, if you add some 6 or 10, you will always be in cyclic prefix, and you will not. Otherwise, if you start here, you'll go into the cyclic prefix of the other guy, which is bad. Okay, is this clear?
Yes.
Okay, so the cyclic prefix also helps you with timing, in the sense that, I mean, it's an engineering issue. It's more not a theoretical issue. It's an engineering issue. You don't have to be so sensitive to timing. As long as you're in the cyclic prefix, you will be able to recover your data. As long as you start your FFT somewhere in the cyclic prefix, you'll be able to recover your data. Okay. So it's already 10:30. I'm going to stop now. In the next class, what is the question, sir? Then there's no option for cyclic prefix data. It should be part of the symbol data itself. Yes, it's absolutely right. Cyclic prefix is always part of the symbol data, copied from the end and put in the front.
That's why I was telling that in terms of reliability, although not in true sense, but the same thing is repeated here. So we are improving the reliability for the reception of the symbol. That is the
yes, sir. The cyclic prefix also is used in timing algorithms. I mean, it's actually pretty useful having the cyclic prefix.
Right. Very good.
Okay. So we are going to stop here. In the next class, I'm going to talk about pilots. How are pilots used in this, and how do you do channel estimation in OFDM? Okay. So with that, I think we'll be in a decent stage of understanding of OFDM, and then we can move ahead to the standards. Okay. So one more thing, I have uploaded a small homework, theoretical problem homework today. There are 4 problems, pretty straightforward problems, except the last problem, which is about a little bit more about pilots and overhead and other things. Please try to attempt all the things. I mean, I have given about a week or 8 days of time. It's going to be evaluated. So I request everyone to just evaluate, finish up the solution and upload it in Google Classroom. Google, you will have a way to upload it. If you have a problem with uploading, please let the TS know. Okay. Thanks everyone. Thank you.
Thank you.
Thank you, sir.